And pruning is like it's a subject that or it's an algorithm that I find really interesting, because there's just so many ways to do pruning, and pruning is like much better. At least I feel that it's a much better algorithm than some of the other algorithms we've seen so far, like quantization, simply because of how powerful it is as a method to reduce your model's complexity. But before okay, so first let's like see what we learned today. So I'll start with a recap of what we've learned previously. Then I'll explain to you what pruning is and also how pruning actually helps us improve performance. We'll also see a demo of how you can use TensorFlow's model optimization toolkit to prune a simple model, and also see how that how pruning affects the performance of the model, and how it reduces the size of the model as well. And finally, we'll end the session with some thoughts that I have about pruning, like some ways that I feel that pruning can be improved, and some of the things that I feel we are doing wrong. Not just me, but the whole community on of researchers working on pruning as well. So yeah, let's start with okay. So before we move ahead, a brief roadmap of the study. So currently we are at session 4. Next session we'll be looking at so far we've been we've been talking about how you can do pruning. Sorry, how you can what edge computing is, and we've looked at one algorithm, which is quantization. Today we'll look at another algorithm, which is pruning. But the next session onward, we'll be looking at how you can actually use some hardware, like work with some hardware at the edge. And then after that, we'll also be looking at some more research topics like early exits and so on. Um, yeah. By the way, we have a Slack group where we, talk about edge computing and all. So yeah, if you, Archana will probably post the link to the Slack group in the chat, and you can join us there. And yeah, this is a QR code for the link to the Slack group. Okay, so like recap, right? So what's the need for edge computing algorithms? And you should know this by now. The one of the major hurdles in deploying models to the edge is that there are power constraints. And what that means is that because normal neural networks, they consume so much power to execute. We don't have that kind of power, capabilities at the edge, or in small devices. So we need to compress our model so that they can be deployed at the edge. Another important, factor for the need for the need for edge computing algorithms is that neural networks are usually trained with single precision floating point values, or FP32 values. They're the same thing. And we train them with single precision floating points because it helps us to increase our accuracy. But that comes at a cost of it making, because floating point algorithm is it's really hard to do in hardware. So that it comes at the cost of speed. And also most edge computing hardware don't actually have any floating point units. So they do floating point calculations very slowly. Um, Another problem is memory constraints. So like Raspberry Pis just have like, or at least the Raspberry Pi 3 had 1 GB of RAM. Other microcontrollers like an Arduino and all, they have even lesser memory. So we have to reduce the size of our models so that they can fit on our devices, on our edge devices. And finally, at the end of the day, if we want to shift to the edge, we want to reduce the latency. Like we don't want to send a request to a cloud server somewhere and then get the result back. So we want to increase our inference efficiency by creating models that don't take a lot of time to execute. And so yeah, just to kind of recap, so our model should be faster. Our model should be smaller so that they can fit on our devices. And one way to make our model smaller is to have models with fewer parameters. And also one way to increase the inference of our system is to have models that can be loaded faster and can compiled faster. And finally, we want to also have some way to preserve accuracy as well. But like I mentioned before, accuracy, it's important, but it's not that important for an edge computing system. We also looked at quantization last week. So remember, quantization in neural networks, it's similar but not the same as quantization that you might have heard when you've been doing signal processing or something. So in signal processing, quantization is kind of used to convert an analog signal, like this red line here, into a digital signal, like this blue line here. And due to that conversion, we kind of lose a bit of precision over here, and lose a bit of data basically. Quantization in edge computing, it's kind of similar. Instead of having like, you can think of the red line as very high precision floating point 32-bit values. And you can think of the blue line as low precision int8 values. So we're trying to do something similar, while actually trying to preserve the accuracy, and the accuracy of the model and the information or the internal representation that the model has learned. Yeah. So usually, so we saw last time, like, right, how we can do how we can just quantize weights, or how we can quantize both weights as well as activations. And what we're trying to do basically is we have this neural network with floating point values. So remember, in like neural networks, the weights are usually centered around 0, and the range is usually from like, I don't know, -1 to +1. And we're trying to take that very small range, with but the precision within that range is really high, and we're trying to take it to this range of -127 to +127. um, so yeah, so the range of int8 is -127 to +128, but we usually ignore the last value so that our range is kind of same in both the negative as well as the positive end. So if we took till 128, we would have one extra value in positive, and that kind of doesn't like it doesn't work that well if we do that. Okay, so I think that's all. That's the recap. If you have any questions, if you have any questions about some of the things you learned last week, feel free to put them in the chat window or in the Q&A window, and I'll take a look maybe towards the middle of the session. But let's get back to pruning. Um, so the concept of pruning is really simple, right? If you have a neural network that looks like this, right, lots of connections in between, that means we have to store a lot of weights, right? For each connection, we have to store a lot of weights. And like if you have like a network that's like, I don't know, 500 neurons and 20 neurons, right? That's already like what, 10,000 weights that you have to store, as well as 10,000 times that you have to calculate something, so 10,000 mac operations. And that's not really, and as you can imagine, like like small devices, they can't really do like so many calculations, and storing 10,000 weights as well takes a lot of space, right? So what people started to do was, they just started to remove some of the connections. So how do you remove connections? You can just set those weights to 0, and if the weight is set to 0, then that weight is not used for inference. So we don't have to do an expensive multiply operation, because multiplying by 0 is 0. So essentially we're removing that connection. We don't have to store that weight. And yeah, we're saving computes, we're reducing the size of our model. And another good thing about pruning is, you can prune your model to just have like only one weight, let's say, like, prune the whole model and it only has one weight. Um, so that means you can prune your models like a lot, right? And you can get a lot of space savings and a lot of computation savings in comparison to quantization, where you can only quantize to, let's say, int 8. So the max that you can save over there is just like 4 times, right? Because you're changing all of your 32-bit weights into 8-bit weights. So you can only save like you can only save like 4 times of your space. um, you can probably quantize further. Like people have started to use neural networks with only 2 weight values, or only 3 weight values, right? Sorry, or like 2-bit weights or 3-bit weights, but those aren't like those don't work really well. So yeah, so the best way to get like a huge amount of savings is like model pruning. um, and yeah, one more thing that I wanted to mention is, you can remove whole neurons as well. So just by like setting the all the weights to that neuron to 0, then you can remove that whole neuron. So there are people who are doing research right now that tries to understand, like which neuron actually plays a role in my output, like a major role in my classification accuracy. And if they find neurons that don't actually have a lot of effect on your accuracy, they just remove that whole neuron. And that's how you can get even more savings, right? But how do you know, like which weights to remove and which neurons to remove? um, so it's actually very simple. And what people do is they just rank weights. So what that means is they take all of the weight values, and then they arrange them in ascending order, and they remove all of the weights that are less than a certain percentage that we call the pruning percentage. So for instance, if you want to prune, like, let's say 10% of a network, then you just remove all the bottom 10% of your weights. So we prune by magnitude of the weights, and the lowest 10% magnitude, we just remove those. We can do this ranking either layer wise or across the whole network. So for instance, we can have like this. We can do this ranking basically for each layer. So that way we can like set different pruning percentages for each layer. So for instance, you might have like a really huge dense layer, right? And you might want to prune that much more as compared to, let's say, like the first convolutional layer in your network, because you don't want to lose a lot of information that the first layer is capturing. So that's how you can get like variable pruning rates across your models as well. um, yeah, and then basically you remove weights. So how do you remove weights? It's very simple. You just set those weights to 0, and that way your weight that way that calculation does not need to happen. And yeah, so we are removing weights, right, at the end of the day. And so we do have to do like a bit of retraining or fine tuning of our model after we prune our weights. um, so that kind of helps to get back some of the drop in accuracy that happens when we perform model pruning. So just to recap, remember we train a normal network that's over parameterized. What over parameterized means is like there's like a lot of parameters and not a lot of them are actually used or are useful. So we first train like this over parameterized model, and then we remove weights, right? And we can remove weights like in many ways. So we can remove like whole networks, or we can just remove like a few weights. But yeah, after we remove all our weights, we then retrain, and we can keep doing this removing weights and retraining until we get like a huge degradation in performance. So we can keep doing this remove weights and retraining stuff. um, and yeah, so So this is like this paper that I found from like I think 2015, which is one of like the first papers that actually implement pruning. And if you remember, like I said, quantization you can only get like at most like 4 times weight savings, right? But here, just by pruning AlexNet, I believe, they were able to get a weight reduction of like 9 times. So their model became 9 times smaller, and at the same time their compute reduction also like the amount of compute they have to do also reduced by 3 times. Another cool thing about pruning is that pruning still uses floating point weights. So the drop in accuracy isn't that high as well. So in this case I think like they found, let's see, yeah, no loss of accuracy. So you're essentially like reducing the size of your model. You're getting all of these advantages without actually any loss of accuracy. I also wanted to explain to you a bit about the importance of weight reduction. Um, so this is like this breakdown of energy that it takes to execute a neural network um, on a hardware, right? I can't recall which hardware this was done on, but for now, like we can forget the type of hardware. But essentially, what this diagram is showing is like so. This is like AlexNet, which has like 5 convolutional and some pooling layers as well, and it has 3 fully connected layers. So in the convolutional layers, you can see that RF, which is register file access. So when we try to get memory from a register inside the processor, a register is basically like this really fast kind of memory. Um, so you can see that there's a lot of memory accesses that's happening, and that memory access takes up a lot of power. Similarly, in the fully connected layer, most of the access happens from DRAM. So DRAM again, it's another kind of memory. It's like a cache memory. So there's a lot of cache, time, like you have to access cache a lot to execute fully connected layers, and access and in hardware nowadays, the bottleneck is actually not not performing operations. It's actually accessing memory. So the ALU is what is responsible for performing operations in a hardware. And you can see that the ALU, the amount of power that we require to actually run this network is like really less as compared to the amount of power it requires to access memory. So read the memory and then load the memory, right? Um, so by reducing your weight by 9 times, we're actually like saving this yellow part and this light blue part a lot. And that's not something that that kind of savings is not something that you can get by just quantizing your model. Um, yeah. So before I move ahead, Archana, I was wondering if there's any questions till now.
Yeah, there are like two questions right now.
Mhm.
One is, so would pruning be done first, the quantization first? Is there any advantage or disadvantage in doing one first then the other?
Mhm. Yeah, that's a good question. And usually you would prune your network first, and then you would perform quantization. I don't, yeah, I don't recall anyone doing it the other way. The reason being, like, of course, like I haven't read any papers about this, or I might have and I can't recall. But the reason being that you want to remove as much of your weights, like as much of your redundant weights and computes first, and then you would want to reduce the size of those weights. So essentially, like if you quantize your network, you're just removing, you're just reducing the precision first, right? But before you reduce your precision, ideally you would want to identify only those weights that are important, and then only quantize those. And that identifying only those important weights, that is basically what pruning is doing. So yeah, I would prune my network first and then quantize it. So later when I show a demo, we actually see this where we prune a network and then we quantize it, and then we see the performance drop as well as the memory savings.
So we have another question: is pruning applied on only fully connected layers? Can we
Hmm.
apply pruning on conv or transformer layer?
Right. So yeah, you can perform pruning on any kind of layer. Like you can apply it on convolutional layers. Um, Transformer layers. You should be able to apply it to transformers as well. Um, Although I haven't seen, like I personally haven't done that, but yeah, it should be possible. Currently, the toolkit that we'll be using, TensorFlow model optimization toolkit, that only prunes fully connected layers, if I'm not wrong. So yeah, that's kind of like a disadvantage of the TensorFlow model optimization toolkit. But I know they're going to support more layers later on. But yeah, you can prune any type of layer. Are there any other questions?
Yeah, we have one last question here. What current real-time application utilizes pruning?
Oh, so lots of applications. If you look at, like, let's say like Edge Impulse is doing like these a lot of wildlife conservation projects where I know they're using pruning of neural networks. Let's see. So for instance, I think Roberta was a bird-based model um, that uh, that used pruning, I think. Um, and then so personally, like in my work, I've used pruning for doing for classifying images captured by neuromorphic cameras. That's also some yeah, pruning. It's a very common algorithm right now, and people use pruning very frequently for their applications. Anything else?
No, but guys, I know this is a little bit of a theoretical concept. We will move on to the actual application of it, or in the sense like at least do hands-on. But I do understand that it might be overwhelming or something that you haven't come across before. But I think like just imparting the concept as such can help you later on, like because it might not immediately strike you where exactly is it used for, or like why do I even learn it. But in the sense when I've seen like when things applications happen or things prop up, you tend to be in this space where you have to quickly learn stuff. So I believe it's better to know things from before, or at least have the concepts, or at least have remotely heard of the concepts before. So don't hesitate to ask us questions. One another thing, we also learned the same way. We were just asking questions a lot, and uh, so don't feel shy or feel like your questions might be stupid. If it's as simple as what is edge computing, we can take that over again. That's completely fine. But do ask us questions, because if you ask us questions, we might be able to help you, and also like it'll help us together in the study group as such. So
Mhm.
yeah, do continue, so.
Yeah, sure. Um, so yeah, I've talked about how pruning happens, but does pruning actually help, right? So you might think about it and you might say, yeah, it should help, right? I'm setting weights to zero. And so, if I set weights to zero, then that means those weights don't have to be read. They don't have to be saved or loaded or calculated, right? So because we are not reading, loading, and calculating those values, we are saving time, memory, we're saving max, which are like operations that we have to do in our hardware. But, are we? Are we actually saving all of these things? Um, Turns out we're not, right? Um, and this is the problem with pruning right now. So even if so let's say, like, you set a weight to zero. You still have to save that zero, in your memory. And saving a floating point 32-bit 0 also requires 32 bits. It's not like you can just put 0 in there and then, that's done. It's not, it doesn't work like that. You have to save it in 32, FP32, in the FP32 standard. So basically you're not actually saving any memory. And reading a 0, it takes the same amount of time, effort, as reading any other floating point 32-bit number. So there's actually no, savings in reading or loading your weights. And finally, does multiplying with 0 actually, is it actually faster than multiplying with other values? And yeah, maybe, but only if the hardware is optimized for it. Um, a lot of times hardwares are actually not optimized for multiplying with 0. So I couldn't, I was doing some research trying to find out if there's any hardware that's optimized for multiplying with 0, or if there aren't, and I couldn't. So a lot of times, you don't even know if the hardware that you're using, for instance, is Intel CPUs optimized for 0 multiplication. I don't know. I couldn't actually find it, which is really weird, because like Intel CPUs are so common. Um, and so yeah, so is there any execution savings? There could be if the hardware is optimized for 0 multiplication. But remember, in the graph that I showed you, the multiplications are actually, they don't really, even if the hardware is optimized for multiplication with 0, um, hardwares are like really efficient at multiplication right now as compared to reading memory. So it doesn't matter. So I was talking with Archana, like I think a few days ago, and I was telling her all of this, and she said, so is pruning just like putting a band-aid on a bullet hole? Does pruning actually, does pruning actually help anywhere? Does it actually do anything? Because if saving the weights to 0 doesn't help save memory, then it's not actually doing anything. And if I still have to read and load that memory, then it's not giving me any savings. And if my hardware is not optimized for 0 multiplication, then that's not saving me anything either. So does pruning actually do anything? It can do something. um, but so remember, the main takeaway here is we don't want to load unnecessary weights, right? That's the whole point of pruning. We don't want to load, and we don't want to save unnecessary weights. Um, and currently, right, if we set weights to 0, what we're doing is we're loading multiple, weight vectors. But these are very sparse vectors. They have a lot of zeros in them. So even though we're loading so many weight vectors, we're only using a part of them, right? So what if, let's say, what if we have like a simple lookup table that just tells me the positions where I should read the weights from, right? So let's say, I have a table that's like um, that just says, 0 1 0 1 0 1, and wherever there's a 0, that signifies, don't read that weight, and wherever there's a 1, that just tells me to read that weight. So that's like a very simple lookup table, and a lookup table like that is very small. So in the hardware, um, so from the hardware's perspective, if we are, if we are not, if we don't, if we only read like a very small lookup table, that's going to be really, really fast as compared to reading like a really large, useless FP32 weight. So yeah, if our lookup table is actually smaller than our weight table, then we can get a lot of memory read savings, as well as memory. We won't have to store those weights anyways. So we can get a lot of savings in that way. And this is like the like a standard that a lot of people are doing even right now, because it tends to work really well. But there's a problem with this method. Most hardwares can't actually do this, like this paradigm of having a lookup table and then reading it very efficiently, right? Because they're just not built for doing that. And finally, like usually when we use CPUs or GPUs or something, there's like this instruction set called SIMD, which is used for doing operations on matrices and stuff, and it's highly efficient, highly optimized, and and this is what is used commonly to run neural networks on your CPUs and GPUs. SIMD instructions, they aren't really optimized for loading and performing multiplications with like sparse weights. So yeah, so say if we can't use SIMD operations, then we have to write our own instruction sets and all, and or we have to write our own instructions, and that's really slow. So the solution here is you have to use custom hardware, right, that can take advantage of pruning. So this is like a custom hardware called EIE, and this is like the PE, which is like the processing element of this EIE hardware. And you can see like so I mean, this doesn't like really seem like anything, but you can see all of the different transistors in here that's doing all the arithmetic operations and saving matrices and so on. Um, and yeah, and the EIE hardware also has like this thing called a zero lookup or something. So what that basically does is it checks whether there is like whether the memory it's trying to read is a zero or not, and if it is, then it just doesn't read it, and it has special logic inside the hardware. So remember, custom logic, that's very hard to write, very hard to build, but it does have it that handles these special conditions with zeros and all very efficiently. Um, so yeah, so the only way, so it's the only way to do pruning, to use custom hardware then. Um, yeah, we can use custom hardware, and this is something that I've been doing my research on in the last like year or so, where I've built my own custom hardware. And believe me, like it's extremely painful to build your own hardware, because it's like it takes a lot of time, it takes a lot of effort, and because you're dealing with things that are like nanometer scale. Um, if you make a mistake during your initial building the hardware, or programming the hardware, programming the flow of logic and so on, then your hardware will not work, and it's just going to be a useless piece of like silicon basically. And yeah, building these hardware, it's really expensive as well, and it can take anywhere from like a year, like 6 months to a year, to actually get back your hardware once you submit it to a manufacturer for making it. So yeah, building a hardware, it's just like this really inefficient process. It's really expensive and it's really difficult. Um, so using custom hardware, it's not the best way to go ahead. It's also like putting a band-aid on a bullet hole, like a different bullet hole. Um, so what people are doing now is they're trying to do something called structured sparsity. So what structured sparsity is instead of randomly removing weights from all over like random places in the weight table, we remove groups of weights. So we can remove like like let's say two weights and then keep two weights and remove two weights, like pairs of weights. Or we can remove like let's say an entire row or column of a filter, or remove like the whole filter itself, right? Um, so by doing this, we introduce something called structured sparsity, where the way that the zeros are present in our weights is structured. Um, and turns out like structured sparsity is really, it's helpful when you're working with SIMD instructions, because it's really fast. SIMD instructions can handle structured sparsity really well, and because you know where the zeros are, so there's also no need to have a lookup table either, since the way you're doing sparsity is going to be constant. Um, but as you might imagine, removing chunks of weights from your neural network will probably like it's probably not good for your neural network. So it does lead to a significant drop in accuracy in your neural network. But the good news is that it's actually now being supported on custom hardware. So hardware is like, let's say the new GPUs by NVIDIA, the 3000 series GPUs, they actually support they actually support structured sparsity, and their performance on, like, when you use structured sparsity, I think nearly doubles. Um, yeah, I think it's somewhere between 1.5 to 2 times the performance when you use structured sparsity. Um, so yeah, so that's, like, that's my introduction to pruning. That, and I also talked a bit about the problems with pruning and how people are trying to solve them right now. Um, if you have any questions till now, I would love
Yeah, we
to.
have one question. So, is there any registry or lookup to find the available hardware that are production ready and that are evaluation ready for Edge or TinyML?
Right. So like the hardware that I showed you, like EIE, that's like a research-based hardware. So only like the researchers who built that hardware have access to it. Um, Apart from that, um, you can buy like a lot of edge computing hardware, like for instance, Raspberry Pis, Arduinos, Nordics boards, Series boards, and so on. These are all like well supported hardware with a lot of good documentation and a really big community behind them. So you can use these hardwares to do edge computing. Yeah. Did I miss anything? Was there a second part to that question?
No, I think that is fine. Then, how much of hardware knowledge is needed to be able to comfortably learn TinyML? I think, like, yeah, sure. You want to take the question?
No, please go ahead.
Yeah. So I think like a lot about. I think it's a mixture of both. I think right now where the field is, you need to know a little of both. Like I don't know, like I'm like comparing it to how deep learning started, right? When deep learning started, everyone was like, you need to know really good math. You need to get your linear algebra straight. If you don't have linear algebra knowledge, you probably cannot get into deep learning. But like slowly we were able to segregate both, and we were able to say that okay, you know a little bit about the algorithm, you know how to model, how to pick a good model, then you could stay in the field. So I think like tinyml is right at the brink right now, wherein we have a lot of researchers who are only working on the algorithm, and we have a lot of researchers who are only working on the hardware too. So I think like obviously like it's a little of both needed right now, but over time I think it will become better. We have one another interesting questions. How binarized, I think you meant binarized, but yeah, how binarized neural networks are used in um, are useful in model compression for edge computing.
Mhm. Yeah. So like binary neural networks are, like, I think the gold standard of like model compression, um, just because of how powerful they are and how easy it is to perform operations on them. Um, so first of all, if your neural network only has two kinds of weights, right? Like a binary neural network, it's only like 0 or 1, or a -1 and a 1. Um, right? It's very easy to you don't have to say like store a lot of like you don't need a lot of memory to store that model, just because you only have two unique weight values. um, and another cool thing about using binary neural networks is that all of the operations on the neural network, like multiplications and additions, basically, you don't need to actually perform multiplications and additions. You can do something called right shift or left shift operations. So bit shift operations. So you can just shift the bit. So like by one position to the left or right, and essentially that could that is like performing an addition or a subtraction. Sorry, an addition or a multiplication or a division. um, and these bit shift operations, so you can actually do bit shift in software as well. So I think in C or C++ you can do bit shifts. Probably, I don't think you can do it in Python. Um, or if you can, I haven't done it ever. But yeah, these bit shift operations are like really, really efficient and really, really fast. Um, And so you're saving like both memory and you're also saving computes. But at the same time, you need like binary neural networks also suffer from the same problem which pruning suffers from, which is you need custom hardware that can perform these operations really fast. So our CPUs and our GPUs are like general purpose. They can perform bit shift operations, and they can save binary weights and all, but they can't do it as efficiently as like they can't do it efficiently enough where we actually can truly um, appreciate how fast we can do these calculations. So we have to continue to use, at least for the moment, custom hardware to actually run these networks really efficiently. um, yeah. Oh, another problem with binary weights is that you sometimes you need like a zero weight, right? And so that's why people have also kind of moved away from binary neural networks to ternary neural networks, which you use three weights. So there's like a zero as well. So the weights are usually -1, 1, and 0. Yeah. Are there any other questions, Archana?
No, we're done for now. But again, guys, feel free to ask us any questions at any time. We would love to answer it.
Yeah. Okay. So demo. Archana, I think you have the
Yeah, I
link.
have pasted the link to the collab notebook on the chat. Feel free to use, like, just click on the collab notebook. It will open it for your own account too.
Yeah.
You just need to have
Um,
like a Gmail account.
yeah. Um, I'm not sure if you can edit the same notebook. I don't think you can. But if you want to edit it, you can click on File and save a copy in Drive. So this will create a copy of the notebook in your own Drive. And yeah, and then you can start to use this use this notebook. Okay, so what we'll do here is we'll try to we'll train like a very simple MNIST neural network, and then we'll try to we'll try to do weight pruning, and we'll see how doing that weight pruning affects the accuracy of the network, and how much space we can save. And finally, what we'll do is we'll take our prune network and then we'll quantize it and see how combining like pruning and then quantizing, how that affects our accuracy, and how that affects how much space the model needs to store. Okay, so the first thing we have to do is install TensorFlow model optimization, which is the toolkit that we'll be using. We have to import some stuff, so TensorFlow, NumPy, and so on. This is like a very simple network. So we have like a conv layer, a dense layer, and we are using it to train on MNIST. We are using like an Adam optimizer and sparse categorical cross entropy. And yeah, finally, we're running fit on our model. So let's see. Okay, so we get a validation accuracy of 98% when we train our network, which is fine. And yeah, we basically we just save we oh, so our test accuracy is almost 98%, and we save the model as well. um, so yeah, so the next thing we'll do is we'll try to prune our model. So there are different ways, like we can do pruning, but the way that is most commonly used and which is supported in TensorFlow right now is low magnitude pruning, which is what we talked about previously as well, where we remove like the weights that have the least value. So we'll initialize that as our pruning method. um, so these are just some hyperparameters that we're setting: batch size, epochs, validation split, and so on. And yeah, so we'll also have to mention the parameters that we're using for pruning. Um, and one of those parameters is the pruning schedule. There are different ways that we can do pruning. So we can, for instance, prune our network where we where we first remove, like, let's say, 50% of all our weights. And then as we train our model, like throughout the training step, we keep removing more and more, weights, and we can end up with like a final sparsity of this of 80%. So remove 80% of our weights. Um, so we can do that, or we can have like a constant sparsity as well, where we train our network with like a constant sparsity of 80%. Um, there are also some other supported ways to schedule how we perform pruning as well. And on top of that, we can also like create our own layer, and our own pruning schedule. Yeah, so we can create our own ways of performing pruning as well. So yeah, once we have set up our pruning parameters and how we want to prune, we can pass our model as well as parameters, and then we can compile that model, and see. So basically, what TensorFlow model optimization does is it converts all of the layers into its pruning specific layer. So here you can see that the flatten has been changed to a prune low magnitude flatten. So it's kind of like how previously we saw that TensorFlow would change like the normal flatten layer to like the quantization specific flatten layer. So in the same way, it's changing it to the pruning specific layer. Um, and yeah, so after that, we train like normal. We also have some callbacks that you can put, that you can like later on see like the summary and of how your pruning happens. But we'll skip that for now. And we can see that our baseline test accuracy was 97.79, and our pruned test accuracy is just 0.5%, like 0.5% accuracy less at 97.21. um so yeah, so even though we pruned like 80% of our network, our accuracy is actually not that hasn't degraded that much, which kind of goes to show how just how over parameterized some of our networks are. We don't need all of those weights, right? So how do we like then the next step is how do we save our model? So before saving, we have to do something called strip pruning. So when TensorFlow starts training a model and so on, it actually saves a lot of internal variables and all, which we don't need. So we have to remove all of those variables. These variables are usually used for training or logging and so on. So we can remove those variables when we save our model because we don't need them. Um, so yeah, we strip that and then we save it. Um, so to save it, we actually save it as a gzip file. The reason we do this is because since there's a lot of zeros in our network, it's actually easier to compress the file as well to get some extra savings. So we can gzip our file as well when gzip our model as well after we've trained it. And yeah, you can see that actually um, our original Keras model was like 78,000 bytes. And after we converted our model to TF Lite over here. And after we convert it to TF Lite and save it as a zip file, we're actually, saving like 3 times our memory. Now, this is where you might be asking, hey, Soham, we're pruning 80% of our model, but we're only getting like 3 times savings. That doesn't make sense. Um, and yeah, you're right, it doesn't. And the reason for that is because of how the model is saved, the different variables that are also saved, as well as, like we still have to, I'm not sure if TensorFlow internally is storing it, is actually still storing zeros in FP32. I'm not sure about that. But if they are, then, that's also an area where a lot of extra space will be, taken up. So yeah, we're kind of we're kind of dependent on the underlying implementation to actually see the advantages that pruning can actually give. Okay, so I hope that kind of makes sense. That like unlike quantization, which is actually really supported right now, like comparatively more supported, pruning isn't. And to actually see some of the advantages of pruning, you have to like go down into the nitty gritty, and then and implement stuff on your own to actually see some of the advantages of pruning. In fact, like some of the papers that I showed you, where people showed, like, there's like 9 times weight savings and 3 compute savings. That's like the theoretical savings. It's not the they haven't actually done it practically. Okay. And next we can combine pruning with quantization. So what we do is we first, like, over here we first specify how we want to do our quantization, and and um, and yeah, this is the model that we want to quantize. Um, yeah, so after we specify that, we can save we basically like save it just to see how much space it takes. And you can see it like takes like really less space, right? So it takes us 8,000 bytes as compared to the 78,000 bytes that our normal Keras model was taking. And finally, this is like a helper function that helps us calculate accuracy. But yeah, once we calculate our accuracy, we can see that our quantized plus, I'm sorry, our pruned plus quantized TensorFlow model has an accuracy of like almost like a similar accuracy. Right? There's like very little drop in accuracy. Um, so yeah, that's that's the demo that I wanted to show. Are there any questions regarding this?
Not yet. I hope it was like understandable. Even if
Yeah.
it's not, I think you can obviously go back and look into the notebook, and I'll try posting it on the channel too. Just like, feel free to ask us questions there and let us know if you can't understand anything. It's okay if you don't have questions right now too. We can, come back to it again and we can answer your questions. The notebook is always there. And if you want to do something cool with it, do let us know. We can also help you out and brainstorm on doing something with this, like this optimization toolkit for this.
Hmm. Hmm. Yeah. Um, okay. So, so the next thing that I wanted to kind of talk about was like some of my thoughts about pruning. Um, and the first thing that I have a problem with pruning is, just give me 1 second. Is how we do the ranking of the weights. So like I mentioned, we just we rank weights and then we remove all the um, low magnitude weights. And this to me is a bit weird because um, you know you're saying that the low magnitude weights actually don't affect the accuracy. Um, and why is it only that the high magnitude weight affects the accuracy? That kind of doesn't make sense to me. Um, and the reason that like in the literature they'll tell you that high magnitude weights will cause, like, when you multiply something with that, it will create like a higher output which has a higher chance of um, affecting the output of the neural network. That's kind of like the standard like reason that people give to like you to only to to prune out the low magnitude weights. But that doesn't make sense to me because if you have a high activation, let's say coming in to a very small weight, then the output of that will be large as well, right? And by pruning that small weight, you are also actually removing the um, removing like preventing that high activation from flowing forward anyways. Um, so what makes sense to me, and this is like research that I've done and a few other people are doing as well, is why not uh, prune based on the activation plus the weights. So we see activations and weights that are similar, and if weights and activations are similar, then we know that output will be really large. So we only prune weights where the activations and weights are not similar. That's something that I'm working on right now. That if you have any ideas on that as well, feel free to reach out. We can do something. But yeah, for to me, like ranking weights, especially like ranking weights and then removing like only the low magnitude weights, that always seemed weird to me. Um, Another thing that is like a really important question right now is bias in these compressed networks. Um, so does pruning these do these algorithms like pruning and all, do they actually cause introduce bias in in the output of the network? And turns out that like there's this researcher by the name of Sarah Hooker. We've actually shared some of her papers in the Slack group as well. So she's done some research, and it turns out that yeah, you know eh, there is actually like pruning does actually introduce bias. So for instance, this is like a paper she released recently. So where she took like a baseline model with 0% pruning, and she was seeing some of the attributes of the classes. So she trained this model on the Celeb A database, which is like a database of celebrity faces. And it also has like classes like the features, so like male, female, young, old, blonde, not blonde, and so on. And so what she saw was like in the baseline model, the false positive rate on average is like 2.73, and the false negative rate is 22.03, right? But when we compress it, our accuracy decreases and so on. So that's normal. So you can expect the false positive rate as well as the false negative rate to rise, which is what happened. But if you see the false positive rate for male, so how often the model identified an image as male has actually increased much, much more as compared to the the aggregate false positive rate, which shows that there's a bias in the model because the model keeps predicting male. And the false negative rate for female has also kind of gone up, which shows a bias, which also shows a bias. So, um, so yeah, uh, like pruning networks actually does introduce bias, and that's a problem, and we're not really sure how to. So right now at least we can understand the issue and we can identify the bias, but we're not sure exactly how to remove that bias. So that's also an area of research that people are working on right now. And finally, what do these compressed models forget? So I know there's like this really weird looking graph here, but basically, what this is so this is on the ImageNet data set, and what this shows is when we have like let's say 50% of our weights pruned, right? You can see that so the accuracy is going to decrease, right? But there's actually like a gain in the class recall for some of the classes. So like wolf spider, right? There's a gain. but there's like a drop in like these in some other classes like frying pan. And what you can see is the more we prune, it turns out that the gain kind of decreases, because you can see like there was more gain over here, and here like fewer models, fewer classes have seen a gain, and there's more so more weights gets pruned. So sorry, more classes have a reduced recall. Um, and in some cases the recall is actually more than, like, the reduction is more than, -5, which is a lot. Um, so yeah. So what and this paper is also by the same researcher, Sarah Hooker. And what the conclusion from all of this is that when we prune a network, the network kind of tries to optimize for those classes that it sees more. And so if there's a class, like, let's say, in the celeb A database, there were more male, I think there were more male images as compared to female. um, and so what happened was, the model tried to increase its accuracy by being more better at classifying males than it was at classifying females. And we see the same thing here as well, where the model kind of compromises on accuracy on some of the low importance, or the classes that appeared less as compared to those classes that appeared more. um, so yeah, just something for you to think about, and some areas of research and some interesting results of pruning. um, so so the first paper, like, where we want to, like, uh, where we want to only prune those weights where the weights and activations are not similar. So that paper is called Scalable and Sustainable Deep Learning via Randomized Hashing. The paper about bias is called Characterizing Bias in Compressed Models. And the paper on what neural networks forget is called, What Do Compressed Neural Networks Forget? Like, the last two papers are, like, really, really interesting, and I would really, like, suggest you to go and read them. Um, and yeah, that's it. Thank you so much for joining. Please join our Slack group. And if you have any questions, I'd love to take them.
Yeah, thank you so much, Soham, for giving such an amazing session. I think we learned a lot today. We have a few questions.
Mhm.
So one is, how much of this code is needed to be written in the regular ML projects, and how much would we be reusing, or using or reusing this kind of template code?
Oh yeah. So you can reuse most of this template code, because this code is only specific to the to how you prune your network. You can change some of the parameters, like, say, you might change like 80% sparsity to 70% and see your result. But yeah, the overall code can be the same. Um, yeah.
Yep. I think a lot about what we talk about here is, critiquing. I just realized that, and that we're very, very critical of algorithms.
Mhm.
And I just realized that, I know that it might not be this important to be this critical when you're deploying, because people don't think about it. But you could just consider it to be like a food for thought.
Mhm.
And yeah, all of these sessions, we have another question here. Will the session be recorded? Yes, the session will be recorded and posted on YouTube. I'll post the link once it's live, like once it's posted on YouTube, onto the group. And one is, what software is used in coding for edge computing?
Yeah. So you can use Python. Um, like, Python will get you like 80 to 90% of the way there. Um, if you really want to go into the nitty gritties and, like, really want to dive really deep and be really optimized, then you can use C. But if you don't know C, I would, suggest like, it's fine. You don't have to learn it. You can just keep using Python.
Yeah.
Sorry.
And we also have like, how do you avoid losing important data which may increase bias due to pruning?
Yeah,
Uh,
like
yeah,
very
sure.
important. I'm sorry. Go ahead.
It's a very interesting question. Thank you so much for posting that. I hope I'm pronouncing your name right, Jessie. And I think like, yeah, like how do you avoid losing important data, right? I mean, definitely the bias in like characterizing bias in compressed model shows that you will end up having a lot of bias. But I guess even I don't even I don't particularly know how would you avoid losing data, right?
Yeah. Um, so if you mean like losing important data, if you mean like how do you prevent the model from forgetting important things that it has learned? We don't know yet. That's an active area of research. If your question is like how do we prevent losing like the training data and all? Um, yeah, so people are doing research on seeing like how training data can affect the bias and the and what neural networks are forgetting. Um, but again, like I'm not sure if there has been any conclusive results on that either.
Yeah.
For now, I think we just know that yeah, there is bias, and we know that there is things that the network is forgetting because of the algorithms, but we don't know how to tackle that problem yet,
Mhm.
unfortunately.
Yep, yep. So yeah, what are some good resources to self learn this? So I think we posted some courses already. You can go on and check it on the group. I've already posted some courses and some books to
Mhm.
start off with. If not, you can reach out to me again and I can give you the links for that too.
Yeah, and yeah, so unfortunately, a lot of what we talk about right now, and a lot of these interesting things that I mentioned, like bias and it's still like research, so you'll have to be comfortable with reading research papers. But don't worry, we'll be doing like sessions on reading research papers as well.
Yeah. So do stay tuned for our next session. So our next session will be held on 18th April, and that we will be covering hardware on the edge. And one interesting thing that we're trying to do right now is figure out ways if we can ship hardware or at least get hardware for people who are coming to our webinars. I mean, it's not done yet, but we are trying our level best to reach out to people and seeing if they will be ready to share their hardware. So yeah.
Yeah.
So when you do post the link, post it on all panelists and attendees. And yeah, that is it, everyone. Thank you so much. And if you guys want to come on stage and talk to us, you can do that too. We have a few minutes to do that. So you can just raise up your hands. I can invite you on stage and let you guys talk and we can talk together if you guys are interested.
Mhm.
If not, I really want to thank everyone for taking out the time today and, talking to us. So yeah, thank you so much. Okay then everyone, bye bye, and feel free to reach out to us for any questions on the Slack group. We really enjoyed the time here today, and do let us know if you have any suggestions, feedback, etc. Bye bye.